Hello. Uh, this is a presentation on the paper Hong-Ou-Mandel interference with structured photons. I am Arnav Jain, and my teammates are Disha Zaveri, Swati Chauhan, Pushti Asher. This paper is by Jauni et al. And it provides a general formalism to calculate closed-form analytic expressions of Hong-Ou-Mandel visibility. So Hong-Ou-Mandel interference is uh, often used for as an experimental technique to see whether the photons that you have are indistinguishable or not. So, for example, if you have two sources where the photons are distinguishable versus the photons are indistinguishable, you will get different sort of interference patterns, and that you can use to check whether the source that you're using are they truly indistinguishable or there is some sort of variation between them, which always happens slightly in an experimental setup, and you can check how much to what extent is that difference. So the formalism that we present is analytic, closed form, general, and is valid for very general measurement setups and takes into account various degrees of freedom a photon can have, like polarization, frequency, spatial modes, etc. So we start with a little back reading on what Gaussian beams are, and because that is used by the paper in their closed form expressions. So the paraxial wave equation, we are going to derive this out. So we start with the regular classical wave equation, del square plus k square e to the equal to 0 for an electromagnetic field in an isotropic and uniform medium. Now, let us assume that this field propagates in the plus z direction. So e to the will have an e power ikz term factor, and that we can take it out by writing it like e to the equal to u to the times e power ik minus ikz. Uh, Now, for a practical beam, generally speaking, there will be some transverse xy variation of amplitude and phase, and what the changes that are there in z direction, there is an e power ikz minus ikz term variation that is very fast, and you have other slower variations. So by taking out that variation, we are uh, we, we will use this property later. So we find the Laplacian, put it back in the original equation. We get this equation. Now, using the fact that the variation is slow, so we can neglect the second order derivative along z. We get this equation, which is called the paraxial wave equation. Now, a general equation to the earlier equation one, this equation, the regular classical wave equation, the solution for a point source as the uh, source is e to the equal to e k power minus I k rho by rho, where rho is the distance from source to the point where the observation is happening. And if we want to find a field distribution near z-axis, so x and y are x minus x naught and y minus y naught are small, and for a value of z sufficiently fast, so z minus z naught is large, I can take z minus z naught square outside of the root and take the binomial approximation, and that will give me rho as this. This is called the Fresnel approximation in this context. And if I put this back in my equation 6 and remove the e power ikz terms, I will get and so in the denominator I keep only the linear term, and in the numerator, since I can remove the e power ikz terms, I will keep until the quadratic term, and I get such a form. Now, this was for a point source. I can define a more general beam with initial radius of curvature r naught. So I define a quantity called r prime z, which is z minus z naught plus r naught for a general beam with initial radius of curvature r naught. So that will make equation 8 true for a general beam with some initial radius of curvature. Now, this beam does not fall off in the transverse directions. That is unphysical. It should decay in the transverse direction and go to zero. So the paraxial wave equation, however, allows for a complex value of r, which will save us here. So I can take x naught, y naught, z naught as complex, and nothing will change. Like it will still be a valid solution to the paraxial wave equation. So if I use this property, I can replace z naught with z naught minus q naught riddle, where I allow q naught riddle to be a complex number. And by this substitution, I get this form if I keep x naught and y naught 0, and q riddle z equal to z minus z naught plus q naught riddle. So if I separate the imaginary and real parts of 1 upon q to the z, I get this. I can separate out like this. They are chosen as 1 by rz and w square for notations purposes, and because w of z and rz are some physical parameters. So rz is radius of curvature, w of z is spot size, also called the beam waist, and this r of z now should be derived from this definition of 1 by q to the z, and not uh, using the original r prime z. R prime z and rz are not cannot be derived, cannot become are not the same exact basically. And now if I substitute back in equation 9, I get this util, which is, as you can see, dying off in the transverse direction. Now, this is the lowest order solution to a larger family of solutions for the paraxial wave equation. If you find the general solutions for the paraxial wave equation by separating the variables out, uh, in that case, in the cylindrical coordinates, you will get Laguerre-Gauss solutions. So, Laguerre-Gauss solutions are these. It's a big expression, but it can be understood. So, W of z is the radius of the beam, and that goes as W naught 1 plus z upon z naught squared. Radius of curvature also has a similar look, so it goes as z 1 plus z upon z naught whole squared. So z upon z naught squared. Rayleigh, we define z naught is called the Rayleigh range, which is 1 upon 2k W naught square, and LLP are generalized Laguerre polynomials. Note that the index L is associated with e power L5, which should give us a hint regarding what L is. So this implies that L is an eigenmode of these modes are the eigenmodes of the angular momentum operator, orbital angular momentum operator, and with the eigenvalue LH cross. And these modes form a complete and orthogonal basis for a fixed beam and waist and curvature. So if I change W naught and like basically I change W naught and these initial numbers, if I change the beam waist and the curvature, they will no longer remain a complete and orthogonal basis. And as we shall see in section 4, they will start to overlap a bit. This is a schematic diagram of a Gaussian beam. This is the beam waist here, W naught. We can see WZ here. It is increasing with time, like with space, as it goes farther along the Z axis. This is the radius of curvature, and this is the Rayleigh range. And this is the schematic diagram of a Gaussian light beam. Uh, Now I will be passing on to Disha, who will discuss more on multimode quantum optics in the second quantization formalism. Thank you.
Right. So to understand how exactly this kind of interference happens, it is important to have background on two basic things. Firstly, we need to understand how exactly we are defining these sort of quantum states. And secondly, we need to understand how these photon states are going to be interacting with different optical devices. In this case, it would include a beam splitter as well as the final detectors. So, starting with describing the photon state, as we all know, a photon can be described as an excitation of the vacuum state. So, basically, when you act the accretion operator on this vacuum state, you're going to get a one photon state. The properties of the basic property of these two operators are given as shown over here. So now typically we don't deal with different degrees of freedom, but in this situation, you have to consider that a photon also has degrees of freedom, including polarization, frequency, and spatial modes. So we need creation or annihilation operators which include these degrees of freedom. Now,
Now,
this would
this would
include the
include the
polarization
polarization
sigma, which
sigma, which
ranges
ranges
from
from
-1
minus
to
1
1.
to 1.
There is
There is
omega, which
omega,
is
which
the
is the
frequency
frequency that
that
spans the
spans
real
the real
space, and
space,
there's a
and there's a
transverse wave
transverse wave
vector
vector
component Q.
component q.
So one
So
can
one
go
can
from
go
this
from this
momentum
momentum
space to the
space to the
position
position
space by
space
doing
by doing
a
a
Fourier
Fourier
transform. Here
transform.
R
Here R
perpendicular is
perpendicular is
basically
basically
just the
just the the
transverse
transverse
radial
radial
direction,
direction,
and
and
hence you
hence you
can
can
write a
write a
single
single photon to be a linear superposition of all these degrees of freedom,
as
as
shown
shown
in
in
this
this
equation.
equation. So now going forward, I will just once explain how to exactly create a general n photon state, right? So, and then I will also show how exactly we can differentiate between these by looking at how the first order correlation function looks, right? So, for n identical photons, essentially
Essentially,
you
you
are
are
going
going
to
to
have
have
the
the
same
same
polarization
polarization
and
and
spatial
spatial.
modes. So it can be essentially, and the degrees of freedom that are associated
With
with
it
it
would
would
then
then
just
just
be
be
the
the
polarization.
polarization, and there would be the two quantum numbers P and L. So we know that G1 is going to be equal to the inner product. No, sorry, the the inner product of A of R perpendicular into psi. So firstly, we can say that we can write A of R, A dagger of R perpendicular as a summation of the LG of the mode operators A dagger PL, and this would be weighted by the LG Gaussian modes, and this can be done due to the orthonormality of the basis. So when you act A of R on this n generalized n photon state, you can expand it into the summation. And in this case, since P and L
And
are
L are
going to
going
be
to be
same for
same
all
for
the
all
n
the n
photons, you're
photons. You're
going to
going to
get
get
the
the
answer
answer
to
to
be
be
root
root
n
n
into
into
LG
LG
dagger
dagger
of
of
LG
LG
dagger
dagger
PL
PL
of
of
R
R
into
into
n
n
minus
minus
1.
1.
And
And
then
then
hence
hence
when
when
you
you
compute
compute
G1,
G1,
you
you
are
are
going
going
to
to
get
get
n
n
into
into
mod
mod
square
square
of
of
LGPL.
LGPL.
So your
So your
intensity
intensity
measurement is
measurement
going
is
to just
going to
show
just
the
show the
typical shape
typical
of an
shape of
LG
an
mode.
LG mode.
But now
But
if you
now
look
if you
at
look
n
at n
photons having
photons having
different
different
quantum
quantum
states,
states,
what
what
happens is
happens is
that
that
you're going
you're
to
going to
have
have
multiple
multiple
different
different
values of
values
P
of
and
P
L
and
that are
L that are
involved in
involved
this,
in
and
this,
hence
and
the
hence the
photon state
photon
can
state
be
can be
shown as a
shown as a
tensor
tensor
product of
product
all
of
of
all
these
of these
different
different
states.
states.
Um,
Um,
in this
in this
case,
case,
now
now
we can
we can
once
once
again
again
write A
write
of
A
R
of
as a
R as a
summation over
summation
all
over
of
all
these
of these
LG
LG
modes.
modes.
Sorry, summation
Summation
over
over
all
all
the
the
APLs
APL
weighted by
weighted
the
by
LG
the LG
modes,
modes,
and
and
on
on
doing
doing
this, we
this,
will
we will
get
get
the
the
following
following
expression.
expression.
So essentially, what will happen is that only the LG modes having the quantum
Quantum
uh, numbers,
numbers,
uh,
uh,
the
the
quantum
quantum
number
number
that
that
is
is
matching
matching
a
a
specific
specific
state
state
will
will
act
act
on
on
that
that
specific
specific
state,
state,
and
and
you're
you're
going
going
to
to
get
get
a
a
summation
summation
uh, that
that
is
is
of
of
this
this
form,
form,
where
where
one
one
where
where
the
the
state
state
which
which
has
has
the
the
matching
matching
P
P
and
and
L
L
is
is
going
going
to
to
become
become
a
a
vacuum
vacuum
state
state
essentially,
essentially,
and the rest
and
are
the
going
rest
to
are going to
remain
remain
ones.
ones.
So
So,
uh,
uh,
thus then
thus
when
then
you
when you
see
see
when
when
you
you
since the
since the
different these number
different
different
number
states are
states are
orthogonal when
orthogonal, when
you
you
compute
compute
G1, the
G1,
only
the
term
only term
surviving
surviving
will
will
be
be
will have the
will have the
creation
creation
operator and
operator and
annihilation
annihilation
operator having
operator
the
having the
same
same
PL.
PL.
So
So
now
now
the inner
the inner
product is
product
going
is
to
going
give
to
a
give a
blurred
blurred
image,
image,
which is
which
going to
is
be a
going to be a
summation of
summation of
uh, the
uh, the
the mod
the
square of
mod
the
square of
different
the
LG
different LG
modes which are
modes which are
involved in this
involved in
n
this n
photon
photon
state.
state.
So
So
here we
here
already
we
see
already see
how
how
there is a
there is a
different
different
kind of
kind of
intensity
intensity
profile that's
profile
going to
that's
be
going to be
formed
formed
for the two
for the two
cases.
cases.
Now,
Now,
coming to
coming
how
to how
exactly
exactly
these
these
photon
photon
states
states
interact with
interact with
optical
optical
devices.
devices.
So,
So,
any kind
any
of
kind of
lossless
lossless
linear
linear
device can
device
be
can be
described
described
using
using
a
a
linear
linear
unitary
unitary
transformation of the
transformation of the
creation and
creation and
annihilation
annihilation
operators as
operators as
shown.
shown.
So, the
So, the
unitary is
unitary is
basically
basically
used so
used so
that
that
to
to
preserve the
preserve the losslessness,
and the
and
simplest
simplest
example is
example is
just
just
this sort of
this sort
phase
of phase
shifter.
shifter.
The
The
one that is
one
going
that
to
is
be
going to be
relevant to us,
relevant to us,
however, is the
however, is
beam
the beam
splitter.
splitter.
So
So
I think
I
we've
think we've
already
already
derived in
derived in
class, but
class, but
essentially,
essentially,
when you
when you
consider
consider
A
a
dagger
dagger
and
and
B
B
dagger to be
dagger
the
to be the
creation
creation
operators of
operators
the
of the
photons
photons
entering port
entering
A
port
and
A
B of
and
a
B of
beam
a beam
splitter,
splitter,
and
and
C dagger
C
and D
dagger and
dagger
D
to be
dagger to
the
be the
creation
creation
operators of the
operators of the
photons
photons
exiting the
exiting the
port C
port
and
C
D.
and
We
D.
can
We can
show
show
that
that
the
the
action of a
action of
beam
a beam
splitter
splitter
is
is
represented by
represented by
this
this
matrix with
matrix with RNT
RNT
associated with
associated with
reflectivity and
reflectivity and
transmittivity of this
transmittivity of this
device.
device.
And of
And
course,
of course,
as
R
mod R
mod
square
R
plus
square
mod
plus
T
mod
square
T
is going
square
to
is
be
going to
1.
be 1.
So
So
in this
in
case,
this,
since we
since
are
we are
dealing with
dealing with
paraxial
paraxial
spatial
spatial
modes,
modes,
you also
you
have to
also have
take
to take
into the
into the
consideration
consideration
that
that
the
the
coefficients are going
coefficients
to
are going to
depend
depend
on the
on the
orbital angular
orbital angular
momentum
momentum
modes
modes
since the
since the
index
index
L
L
changes sign
changes
after
sign
getting
after getting
reflected.
reflected.
Thus, you are
Thus, you
going
are
to
going to
have
have
to
to
we
that
see
we see
that
that
B has
B has
a
a
minus
minus
L
L
comma P
comma P
and C
and
also
C
has a
also has a
minus L
minus L
comma P.
comma P.
So for
So for
example, if
example,
we
if
just
we
want to
just want
see
to see
AL,
AL,
you have
you have
R
R
star
star
into
into
C
C
minus
minus
S.
S.
So
So
over
over
here
here
R
R
is
is
showing the
showing the
reflection.
reflection.
So we are
So
seeing
we are
that
seeing
there's
that
a
there's a
change in the
change in
sign
the
of
sign of
orbital
orbital
angular
angular
momentum,
momentum,
while then
while
when
then when
V
V
um
um
is
is
multiplied with the
multiplied with the
transmission,
transmission,
you see
you
that the
see that
change
the change
isn't
isn't
existing.
existing.
Right.
Uh,
Okay,
okay,
so
so
now
now
hence you
hence
can
you
see
can
that
see that
basically this
basically
beam
this beam
splitter can
splitter
act
can
like
act
a
like a
single
single
qubit
qubit
gate,
gate,
which is
which is
important for
important for
most
most
quantum
quantum
protocols.
protocols.
So
So
the only
the
thing
only
that's left
thing
now
that's
is to
left
see
now is
how
to see
exactly
how
this is
exactly
getting
this is getting
detected.
detected.
So
So
now
now
the
the
action of
action
any
of any
detector can
detector
be found with the
found with
help
the
of a
help of a
measurement
measurement
operator.
operator.
So when we
So
are
when we are
performing a
performing a
measurement on a
measurement on a
quantum
quantum
system,
system,
the
the
probability of
probability of
detecting
detecting
a
a
photon is
photon
given
is
by the
given by the
trace of
trace
that
of that
measurement
measurement
operator
operator
into the
into the
density
density
matrix of
matrix
that
of that
state
state
of that
of that
system.
system.
So
So
basically,
basically,
there are two
there are
types
two
of
types of
detectors I'm
detectors
going
I'm
to
going to
discuss,
discuss,
and that is
and
going
that
to
is
be
going to be
discussed in the
discussed in the
paper.
paper.
Firstly,
Firstly,
there's a
there's a
bucket
bucket
detector. So
detector. So
bucket
bucket
detector
detector
is
is
insensitive
insensitive
to
to
all the
all the
degrees of
degrees of
freedom.
freedom.
It
It
basically only
basically
measures
only
whether
measures
there is an
whether there is an
incident
incident
photon
photon
present or
present
not.
or not.
Hence, it
Hence,
can
it
be
can be
given as
given
a
as a
summation
summation
over all
over all
polarization and
polarization and
integration
integration
over
over
all
all
the r
the r
perpendicular
perpendicular
over
over
d square
d
r
square r
perpendicular,
perpendicular,
and
and
yeah,
yeah,
essentially it
essentially
can
it
be
can be
given by
given
this
by this
state.
state.
Similarly,
Similarly, if we want to,
if we
if
now
we
take a
now take a
detector that
detector
is
that is
sensitive to a
sensitive
very
to a very
specific
specific
spatial mode,
spatial
for
mode, for
example,
example,
LGQM,
LGQM,
the
the
action of the
action of the
detector will
detector will
project only
project
onto
only
the
onto the
spatial mode,
spatial mode,
and it
and
can
it
be
can be
shown
shown
by
by
the
the
outer
outer
product of
product
the
of the
state
state
1QM.
1QM.
So this
So
is
this is
different
different
from
from
like the
the
insensitive case,
insensitive case,
because here
because
it
here it
is
is
going to
going to
basically sum
basically
over
sum
all
over all
QM
QM
states. Here
states.
it is
Here it
only
is only
considering one
considering one
specific
specific
QM,
QM,
and then
and
on
then on
expanding, we
expanding,
will
we will
find that
find
this
that this
state
state
becomes as
becomes as
shown.
shown.
So
So
now
now
basically we
basically we
have all
have all
the
the
necessary
necessary
background to
background to
understand how
understand
these
how these
HOM
HOM
effects
effects
occur,
occur,
and
and
to
to
understand how
understand
this
how this
HOM
HOM
effect will
effect will
occur after these
occur after
different
these different
detection
detection
conditions, and
conditions,
this is
and
what
this is what
Swati is going
Swati
to
is
be
going to be
explaining.
explaining.
So,
So,
just to
just to
show a
show a
diagram of
diagram
how
of
an
how an
experimental
experimental
setup could
setup
look
could
like,
look like,
we have
we
over here
have
a
over
beam
here a beam
splitter.
splitter.
This is the
This is the
first
first
case
case
where we
where
have a
we have a
multi-mode,
multi-mode,
multi-mode
multi-mode
fiber.
fiber.
So
So
essentially,
essentially,
the beam
the beam
splitter has
splitter
two
has two
input
input
ports A
ports,
and
A
B,
and
and two
B, and two
output ports
output
C
ports,
and
C
D.
and D.
Each
Each
output
output
port has
port has
um,
um
a five has the
has the
fiber
fiber
coupling that
coupling
leads
that
to the
leads to the
detector,
detector,
and then this
and then
detector
this
is a
detector is a
multi-mode
multi-mode
fiber, so
fiber,
which
so which
essentially means
essentially
it's a
means it's a
bucket
bucket
detector, and we
detector,
can
and
see
we
it
can
as a
see it as a
summation.
summation.
The
The
second
second
case is
case is
basically
basically
considering
considering
um,
um,
two
two
single mode
single mode
fibers.
fibers.
So
So
basically over
basically
here
over
the
here the
detection
detection
happens
happens
only for a
only for a
specific
specific
mode,
mode,
and the
and the
third case
third
has
case has one mode,
one
one
single mode
single
and
mode
one
and one
multi-mode
multi-mode
fiber.
fiber.
Swati will be
Swati will be
explaining how
explaining how
exactly
exactly
Hong-Ou-Mandel
Hong-Ou-Mandel
interference
interference
happens in all
happens in
these
all
three
these three
conditions.
conditions.
Handing over
Handing
to
over to her.
her.
First of all, we'll start to um, talk about the polarization and frequency degenerate photons. So let's start with input state description. So we are focusing on the simplest case of two photons which are prepared in product stage, where each photon enters the beam splitter from a different pole. Let's assume that the photon entering port A is in the spatial node psi 1 and the photon entering port B is in the spatial node psi 2.
and it can be written as psi1 and cross product with psi2. Now let's talk about creation operators. So we know A cap dagger alpha as a creation operator for photons entering port A in node alpha, and B cap dagger beta as a creation operator for photons acting for beam mode beta. If alpha and beta correspond to transverse position, then we can write this thing. We can write psi1 and psi2 as this. Then here we are using this notation for writing the Hermitian product in the space of complex functions with integrals square. Now let's talk about general input state formulation. And so we can write the full input state as uh, summation over alpha beta psi1 alpha psi2 beta a cap dagger alpha b cap dagger beta z and action of the beam splitter. So we are taking the simplest case where 50-50 beam splitter is acting on the input nodes, which as follows. So a cap dagger alpha is written as 1 by root 2 c cap dagger alpha plus d cap dagger alpha, and b cap dagger beta is written as 1 by root 2 c cap dagger beta minus d cap dagger beta. Here C and D refer to the output nodes of the beam splitter, and the output speed after the beam splitter is given by summation over alpha beta psi1 alpha psi2 beta 1 by 2 c cap dagger alpha plus c cap dagger alpha c cap dagger beta minus c cap dagger beta and measurement part. So coincidence counts at output nodes. So in a typical Hong-Ou-Mandel experiment, we measure the coincidence counts at the output nodes C and D of the beam splitter. And we define the transition operator at port C as this. P gamma can take two values, 0 and 1. And from the property of projection operator, we have pi cap square is equal to pi cap. So now let's talk about coincidence measurement operator, which is pi cap CD, which is written as this. And then the measurement output is given as RCD, which is stress of rho cap output and pi cap CD, which can be expanded as this. And then we got this expression. So we have three cases, which the first one is two bucket detectors. So if both detectors in arm C and D can collect a large number of nodes, then we have P gamma CD is equal to 1 for each node gamma. And the coincident rate becomes 1 by 4 gamma gamma prime, psi1 gamma prime, psi2 gamma minus psi1 gamma, psi2 gamma prime, which can be written as this. And then if we take psi1 gamma psi1 gamma mode square is 1 and psi2 gamma mode square is 1, then we get RCD as this. Then they single mode detectors. So for single mode detectors, we have P gamma CD delta gamma eta, and the coincidence rate is RCD is 1 by 4 psi1 eta C psi2 eta D minus psi1 eta D psi2 eta C. And the third case is single mode detector and bucket detector. So in a hybrid configuration where one detector is single mode and the other one is bucket detector. So we have P gamma is delta gamma eta and other one P gamma D is 1 for all gamma. So we have RCD is 1 by 4 summation over gamma psi1 gamma psi2 eta minus psi2 gamma psi1 eta whole square. And if we use completeness condition, then we have gamma is I cap. So now the last part is in relation to correlated input states. So for now separable input states, psi 0 is this, and the coincidence rate becomes this. And for arbitrary transmissivity, the expression is this. And this highlights how imperfect visibility can arise due to differences in reflectivity, transmissivity of the beam splitter.
Hello, I'm Pushti. So let's move on to section 4. So section 4 addresses a critical challenge in HOM experiments, quantifying spatial mode overlaps when two photons have mismatched LG parameters. The visibility of HOM interference depends on the inner product psi1 psi2 between the spatial modes of the photons. This section particularly derives analytical solutions for these two scenarios. The first case is the same LG basis, where they have identical beam waves W naught and propagation distance is Z. So when both photons share identical LG parameters, orthogonality simplifies the overlap to a sum of coefficient products, which is this. So here ALP1 and ALP2 are expansion coefficients of the modes in the same basis. The Kronecker delta collapses the double sum into a single series, preserving orthogonality. Now case 2 is different LG bases, which is because of the mismatched W naught or Z, leading to a non-trivial integral solved via Hilbert geometric function. So for mismatched beams, the overlap becomes a complex radial angular integral. So while solving the integral, there are two key steps. One is the azimuthal integration, which is this section over here, and which yields which yields the delta LL dash enforcing OM conversation. The second step is the radial integral, which reduces to this, where x is equal to p square, and sigma is this value right over here. Uh, so sigma combines beam curvature and Gauy-Fils differentials. The final analytical solution resolves to this, where gamma is the gamma function which manages the factorial terms from the Lagrange polynomials. The 2 often is the hypergeometric function encoding radial mode coupling, and the sigma is a complex parameter sensitive to beam waste and curvatures. The figure right here illustrates how HOM interference geometry for input photons having different mode parameters. Now we have implemented the code uh, to to s- to look at the functions of LG overlap analytical numerical functions and compare it using heat maps. So the function in a product of LP L dash P dash computes the whole analytically. So let's walk through the steps. So first, this is the function LG overlap. So the fixed waist W1 equal to 1. Uh, this is the parameter setup. We get fixed waist W1 equal to 1 and variable waist W2 equal to W ratio into W1. Uh, for for Z naught, we have put the Rayleigh ranges, that is Z naught equal to 0.5 W1 square to Z naught dash equal to 0.5 W2 square. Now the sigma calculation is done here, which sigma real part is calculated here and sigma imaginary part is calculated here. For the normalization factor, we have derived it using the gamma functions. And the hypergeometric argument, which computes the sigma, which computes it using the equation right over here. So the final overlap combines terms and returns overlap dash square, overlap mode of overlap square using SciPy integral hype 2f1. So now that we have the function, we lay on the parameters and then we plot the function. So for this is the figure 3a, which shows the diagonal dominance at w2 by w1 equal to 1, and hence preserves the orthogonality, the bright diagonal, and the off diagonal spread for the ratio 0.5 and 0.7, which shows the radial mode leakage due to phase mismatch. For figure 3b, the propagation mismatch at z equal to 0, orthogonality holds, that is the bright red, bright yellow spots. And for z by z not equal to 0.5 and 1, wavefront curvature differences induce p is not equal to p dash coupling. Now we move on to the figure for to plot the figures 3c and 3b. So for that, we have to introduce a new function of the LG overlap in numerical, which directly integrates equation 32 using adaptive quadrature, that is scipy dot integrate dot quad. Now the integrand evaluates 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 the evaluates this thing right over here, and it evaluates directly, so that, and then we also have a normalization factor which matches the analytical factor A. Next we have timing analysis. The time evaluation function benchmarks 100 runs for varying w2 by w1 or z by z0. The key findings is that when we plot it, we see that the analytical solution is 100 to 1000x faster than the numerical integration, and it is mainly because of the hypergeometric functions, and they bypass the iterative radial integrals. So now we see here, we compare the numerical and analytical formula. So analytical methods enable real-time parameter sweeps for AI-driven quantum experiments. Um, we have a lot of experimental implications for because of this. First is alignment sensitivity. It says that a 10% waste mismatch reduces HRM visibility by 30% for p equal to 1 points. Second is radial index engineering, which enables tailored mode couplings for OM based quantum communication. Third is AI driven design. Fast analytical solutions allow neural networks on high dimensional spaces. We conclude section 4 here. Uh, the section 4 provided three main things. One is the closed form formula for HM visibility under B mismatches. Second is computational tools for optimizing spatial mode experiments. And three, scalability for next generation quantum optics. This framework bridges theory and experiment, exemplified by its use in computational quantum photonics to align structured photon experiments efficiently.